Well, let's look at number 4. We've got a 10 kilogram box. I like to put that right into the picture. It's released from rest. That's important. It has no kinetic energy. It slides down the 800 centimeter. I'll make that 8 meter, and again, I'll put that right in the picture. Uh, Tall incline, then it compresses a spring down here. The spring constant, I'm going to put that in there as well. It'll help you think about it. And what's the maximum compression? That is X, so I'll put that in there as well, before being pushed away. So it'll be pushed all the way in, and then it'll turn around and go the other way. What's the maximum compression? You've got a height change, you've got velocity changes, you've got energies over here. This is obviously an energy problem if you've got velocity and height changes. What's the concept here? Oh, there's one more thing. All the surfaces are frictionless except right here where the this is 10 meters, and the coefficient of friction, I'll put that here as well, is 0.10 unitless. So what is this? This is a situation where you've got energy changes, but there's work on the system. And we remember that if there's no work done on my system, the energy here would be equal to the energy here, but it's not. When work is done on my system, in this case, the only work done on my system is friction. The work done on my system equals the energy change as well. What energy change did you have? It had a velocity. It had uh, it had no velocity there, and it had no velocity here. So there's no KE change. So we'll just say that's zero. But there is a PE change. There's a gravitational PE change. And also at the end, there's a change in elastic potential energy, or the potential energy of the spring. So that's the only change. Let's put the delta here, and there's a change here. So once again, when there is work done on my system, it's equal to the work done on my system, which is negative work, of course. It'll equal the two energy changes, and that's just an equation you have to remember. Any work done on my system is equal to the two energy changes. So we've got a lot going on here. So I like to pull out different things like, well, I'll look. What's the work on my system? That is the friction times the D. Now, because it's working at 180 degrees, to displacement's going this way, friction goes that way. So it's negative FD, cosine 180 is negative 1. So the friction is mu. It's a flat surface. There's the friction times the D and the work against friction. So it's good to do it separately. The friction is mu, is 0.10 times the weight, which is 10 times 10 is 100 newtons. This was the mass. So 100 newtons times the distance, which was given as 10 meters. I look at my picture, 10 times 100 is 1,000. So the work that's negative done against friction is, uh, negative 100 joules. Okay. Now, what about I think I'd like to also pull out the change in gravitational potential energy, which is, it's a negative change, right? It started out really high and went to zero. So the M is 10 kg. M times G, 10 meters per second squared, times the delta H. Be careful, the change in delta H is negative 8.0 meters. It's a loss of height. So 10 times 10 is 100. Negative 800 is the delta PE. Joules, that is, it's energy. And the last one is, for a spring. It's been a while since we did this, but the PE of a spring is 1/2 kx squared. That's going to be a gain. There was no, in the very beginning, there was no elastic potential energy. And at the end, we have an increase in elastic potential energy. So let's put this stuff in the equation. The work done against friction is negative 100 joules. There's no kinetic energy change. There's a potential energy change of negative 800 joules, and now what do I want? Let's go back to what I want. I want X, and if I'm going to find X, I better find what the PE of the spring is. So delta PE of the spring. So you add 800 to both sides, positive 800 to both sides, and you get 700 joules equals the change in elastic potential energy or spring energy, which equals 1 half kx squared. So 700 joules is 1 half k, which is given as 50 right over here. Newtons per meter is the unit always, times the x squared. I multi 1 half times 50 is 25. Divide both sides by 25. Well, let's just do it this way. 25x squared equals 700. And I just flipped it around. That's joules. And divide both sides by 25. Take the square root. Go to two significant digits. And you get this. Whoops, not meters per second. It's a compression of 5.3 meters. Beautiful. Okay, good. All right, next problem. This is a 10 kilogram box held against a spring, compressed against a spring. Uh, it's compressed 2 meters, so x is 2.0 meters. As shown, if the box is moving at 10 meters per second, I'm going to put that right into the when it reaches the top. So at the top, it has PE and KE because it has a non-zero velocity. 10 meters equals the top. What is the spring constant? All surfaces are frictionless. You know what? No work is done on my system. So the PE here, which is spring PE, it's on the bottom. It has no gravitational PE. Its height is zero. It has no motion in the beginning. So in the beginning, it's all spring PE, and up here, it turns into gravitational PE and kinetic energy. So this is the old stuff. This is the conservation of momentum. The total energy before equals the total energy after because no work is done on or by my system. So mgh plus 1 half mv squared equals 1 half the equation for elastic potential energy. And I'll multiply everything by 2. 2mgh plus mv squared equals kx squared. Then I'll divide. What are we looking for here? Let's see. What is the... Okay, oh, the height is 6 meters, by the way. That's your h. Um, we are looking for... Um, what's the spring? Oh, what's the spring constant k? So I divide both sides by x squared, right? And I'll get my k value. So this is going to give me the answers. When I plug in the numbers, I've got the m is 10, so 2 mgh, 2 times 10 kg, mg times 10. I don't think I'm going to run out of room if I do it over here. Let's do it over here. So squeeze it in. So 2 times n, 10 kg, times gh, so 10 meters per second squared, mgh, what's the h here? H is, I should have put that in my picture, 6.0 meters. Okay, that's mgh plus m10 kilograms times v squared. V squared is 10 meters per second, and that gets squared. All of that, whoops, mgh, it goes like that. So yeah, mv squared, all of that over x squared, which the x is given as, let's look at the picture, is 2 meters. So 2 meters squared. So now it's a math problem. Let's say, Harry, it's this over here. So answer is that the k value is 550. I'm going to double check this. Newtons per meter. Let's see if I got the right answer. I'm going to pause this and check it. All right, it checks out. Double checked it. Okay. And this is something that's just like a lab we're going to do. There's a system with the above, someone holds this over here and then just lets it go. So the weight falls and it drags this box along. What we want to find obviously is the mu. System was released. Okay. This is when the suspended mass has fallen um, 8 meters, then the both blocks have a speed of this. How much gravitational PE did the suspended box lose? It didn't really lose. That's why I put in parentheses. It just went to the system. It caused the system's energy to go up. Now, so how much did it lose? Well, okay, I know what the PE equation is mg delta H. So this is M is 6 kilogram. The only thing falling is the 6 kilogram box. M times G times H. We're told the H. Let's put the H in there. It falls 8 meters. So that's a loss of 8 meters. Put our meters. So that's 60 times 8. 60 times 8 is it loses. Sorry if it got a little sloppy. That's 10, and that's 8.0. 6 times 10, 60 times 8, it loses 480 joules of PE. Of course, it gets not doesn't really lose; it gets transferred to the system. Where did the uh, gravitational potential energy go? Ignore air resistance. Where did it go? Well, the KE of both blocks increase, right? So that's what by falling down, not only the KE of the 6 kilogram and the 4 kilogram, they both increase in velocity. You have to be really careful not to say just the one on the table increases. And where else did it go? Some of it went to work against friction. So the table got hotter, the block got hotter. So the kinetic energy went to changing the kinetic energy, and some of it was lost through that negative work for friction. So there's a loss in kinetic energy. I'm sorry, gaining kinetic energy, excuse me, and there's a loss of energy through friction. So what is the kinetic energy of both blocks? So now we've got to, when the mass has fallen 8 meters, now we've got to employ our technique. But because we have work done on our system, the work of friction equals the change in kinetic energy plus the change in potential energy. When work is done on my system, the energy of the system changes. How much does it change? Well, it depends upon the work done on my system. That's quite negative work. Let's see. Here's another instance where we kind of do all the work off to the side. So let's see what we can do. Let's go back to the picture. Um, you don't, interesting, you don't have, what is the, what is the kinetic energy of each block? Oh, what am I talking? What is the kinetic energy of each block? Um, that is quite easy. What is the kinetic energy? We don't even use this because it's simple enough to go. Kinetic energy is 1/2 mv squared. So for the block, so let's do it for the 4 kilogram block. So the 4 kg, that would be um, the kinetic energy is 1/2 4 kg times the velocity that they gave you, which is 8 meters per second. The whole system is moving at 8 meters per second. That's squared. So 1/2 of 4 is 2 times 64. So that's the kinetic. So it's 128 joules for the 4 kilogram block. Um, so how about the other block, which is 6? It's also going that speed of 8 meters per second, so 6 kg. So I did not use this, not yet. 6 kg, Ke equals 1/2 mv squared equals 1/2 m, 6 kilogram block, times the v that was given, 8.0 meters per second, but that is squared. That's 64. Half of 6 is 3. 3 times 64 is 192 joules. So you got this block and this block. Each block is there. So the total energy gained is right here and here, isn't it? How much energy did the frictional force take away from the system with negative work? All right. How much energy the friction? Okay. So how much energy did the frictional force take away? Well, that negative work, they say, well, here's now we can use the WF, the work done against friction, that's going to be, we know it's going to be negative. The gain equals the gain in KE plus the loss of PE. So the work done against friction was, what was the gain? We just add up these two numbers. And 192 joules plus 128 joules. That's the gain in KE because we figured out each one. Plus the loss in the PE. Okay. Did we do that? No, we did. Oh, wait, we did it right over here. This is how much PE was lost. So negative 480 joules. So when you do that, you combine the two, you get that this much work was done by friction, that this much negative work. No surprise, this number is bigger than that number. By this is more negative than that number by negative 160. That is the work done by friction. So that when work is done on or by my system, it equals the energy changes. One energy goes up. Which energy goes up? The KE goes up. The PE goes down. And the difference is the work done against friction. What was the frictional force? Okay, we got the work done against friction. Isn't that just friction times D? What was the frictional force? Well, it moved. We're told that the box moved 8 meters. Do you remember that? This box slid 8 meters, but where is right there? 8 meters. So it slid. We should put that in the pictures. Slid 8 meters. All right. So the negative 160 joules equals the friction times that movement of 8 meters. I think they really mean 8.0 meters. I'm going to put 8.0 meters. And so you divide both sides by 8, and the friction is a negative force because it's opposite the direction that we call positive. And what is the coefficient of friction? Well, it's a horizontal surface. Thank you. Equals negative 20 newtons. Um, equals mu times Fg. Now this negative doesn't matter because this mu is never going to be negative. So it's 20 equals mu, which is unknown, times the block was 4 kilograms, and that probably should have been 4.0 kilograms. So that turns into, let's make that 40 newtons. 4 times 10, divide both sides by 40, and the friction is 0.50. With, whoops, the coefficient of friction, wrong, is 0.50, unitless number. So there you go. I'm going to stop right there. So why do we use work equals the change of energies? Because there was friction. They mentioned friction. So the energy before is not equal to the energy after. It's good to pull away when you do. I made a mistake over here and used this. When we want to find the work done by friction, well, the work done by friction equals the two energy changes. And so let's stop right there because that's a lot already.